Hello and welcome back to my channel. In this second video we will examine the quality of the ultrasonic sound source and microphone combined, and some issues related to frequency inversion. First of all, I'll present a functional block diagram of the essential working parts of the ultrasonic listener. And one of the key components of the listener is having an ultrasonic sound source, which in this case happens to be a bat. Second key component is a ultrasonic microphone pickup. Now, in the ultrasonic frequencies of 60 kilohertz or higher, it's questionable whether the sound can actually travel from the bat to a microphone if it's more than a few feet away. It generally gets absorbed in the air. We need a preamplifier with a gain adjustment. I'm using a color coding here, where blue is the functional block diagrams, functional components of the ultrasonic listener, and the outputs of the various stages of the ultrasonic listener are shown either in red or green. And I've chosen red to represent the time signal, time variation, time domain variation of the signal, and the green graphs represent the frequency domain representation of the time signal. So this would be the spectrum representation of the emitted calls from the bat that consist of a band of frequencies from a low to a high, and down here we have the local oscillator, the device that emits the modulator frequency, that's shown as a single spike on the frequency spectrum of F naught. In this case, F naught is not the fundamental frequency of the Fourier transform of the spectrum here, but it's used as a local oscillator frequency. So it's a sine wave oscillator that just repeats from one cycle to the next and on to infinity. Signal from the preamplifier, sound signal, which is generally in the ultrasonic range, is fed into a mixer modulator, i.e. multiplier. Second input is the local oscillator, and the output of the mixer modulator is basically a sum frequency spectrum and a difference frequency spectrum. And the local oscillator frequency falls right in the geometric center of these two. These are called, in the radio lingo, sidebands, upper sideband and the lower sideband. The one of interest to us will be the lower sideband because it's where all the audible frequencies are contained. Now, you'll see that in these mixer hardware electronics, some of the local oscillator frequency might feed through, which is undesirable, and a lot of the manufacturers of this hardware provide a means of null adjusting the local oscillator, also called the carrier frequency in radio lingo, down to a minimum, or I don't know if it can go down to zero. The next step of the signal processing circuitry would be a low-pass filter to remove the upper sideband, the sums frequencies that we don't want to listen to. We can't even hear them, but they will, add to load the audio amplifier. So the output result of the low-pass filter will just be the difference frequencies as depicted here in the spectrum, Fourier spectrum. So FL minus F naught sets the bottom limit, low frequency of the difference frequency band, or lower sideband. FH minus F naught sets the upper limit. So the output of the low pass filter is fed down here into a volume adjustment potentiometer and an audio amplifier, and subsequently that output can be taken to a microphone input of your camcorder or audio power amplifier to power your headphones or a small speaker. So that's about it as far as the functional blocks of the listening device go. While adjusting the local oscillator frequency, it's generally desirable to maintain the oscillator frequency less than or equal to than the lowest frequency in the spectrum that is being modulated. Now that's not always possible, and whether or not while listening to a BAT call it's important, it may not be that important, but in a subsequent video or segment of this video I will explain what happens when F naught becomes greater than FL. And we get some strange effects, like you might have heard me speaking the poem Mary Had a Little Lamb in the first video, things of that nature. Okay, first of all I'm going to talk about powering up the various integrated circuits that comprise the ultrasound listener. And what I have is a power supply that's capable of split supply mode and even has an auxiliary 5-volt output here. Now I'm not going to use this power supply in split mode. Many op-amps are usually powered by split power supplies, but what I am doing is using a single supply of 12 volts and ground, negative. And the reason for that is my goal eventually is to use this gadget either with a 9-volt battery or maybe a 9-volt and 2 AA's for a total of 12 volts out in the field. So it's not very convenient to use split power supply. And as I go along, I will be describing the various circuits and how I bias the op-amps and so on for single supply operation. The microphone, the Electret microphone, Max 4466 is the number of that one, requires a 5-volt power. So this, as stated earlier, this power supply is capable of producing that. It has a dedicated output with just 3 settings. Right now it's set to 5 volts, and that's another common ground point, and that's the power for the little microphone that will be showing you very shortly. So starting our discussion on the signal chain that was shown on the whiteboard at the very beginning, we need a source of ultrasonic sound. Now, unless you have a bat flying around overhead that may not cooperate, I do have a couple of sources that I will substitute for the bat. Well, here's the first one. A wine glass. That might do it. Another one. A jar. I think that also might do it. So no real animals were harmed in producing this film. Okay, in this segment we will test our ultrasonic sound sources and display the results of those tests on the oscilloscope. So essentially we're trying to find out how good is this wine glass and the jar as a source of ultrasonic sound. And since I have my microphone and preamplifier and oscilloscope already hooked up, everything is breadboarded, and I'm explaining all the pieces as I go along, but essentially everything is functional, and I can show you all these things in full operation. Okay, so here goes the wine glass. Okay, so there's the frequency spectrum on the oscilloscope, and just to get our orientation and bearings. So what we have is the 20 kilohertz center right there. 0 is there, and each division is 5 kilohertz. 5, 10, 15, 20, 25, 30. So if you observe, there's quite a bit of audible frequency spectrum from the almost 0 to 20 kilohertz. Of course, we can hear the wine glass being struck, and there is a little bit 5, 10 from the 20, 25, 30. So from 20 to 30 kilohertz there appears to be some ultrasonic spectrum. Now it's quite possible that there is more up here beyond the 30, as I can see a few faint spikes there. It's just that our microphone that I'm using, the Max 4466, does not have the frequency response to pick up anything higher. Okay, so that's the wine glass. Now let's see how the jar fares in comparison. So set the oscilloscope up back to single triggering and sampling. Oops, it triggered on something I did not want. Okay, here goes. Okay, there it is. Quite a bit of audible range, although there does not seem to be, there is some, yeah, between the 20 and the 30 kilohertz region. Almost, it's almost the same as the wine glass. But yeah, like I said, this might be a limitation of the microphone I'm using, and I'm not set in stone to carry it through to completion. It is only for the initial tryouts, and it seems to be serving that purpose. Okay, hello, and we're back here in MathCAD. So what I'm going to do now is do a numerical simulation of the case where the modulating frequency exceeds the lowest frequency of the spectrum, and perhaps even exceeds the highest. So we'll look at a couple of cases, and we'll see what happens to the difference frequencies, what they look like in that case. So now we've seen the frequency spectrum of the wine glass and the jar being struck, and we have an idea that more or less the low frequencies start off higher, and the higher frequencies start off at lower amplitudes. So I've simulated that in this MathCAD file by representing my 4 sine wave oscillators at amplitudes of 4, 3, 2, 1. Okay, so let's go down the screen and have a look at what the input spectrum looks like, or unmodulated spectrum. There they are. This one is supposed to be of an amplitude ratio of 4 compared to that one, but somehow it's not turning out that way. And let's have a look at the spectrum of the modulated signal. Okay, so these are the difference frequencies, and we'll notice that a couple things have happened here. Since the modulator is set at 18 kilohertz, which is higher than the 2 lowest frequencies on the input spectrum, and here they are in graphical form, that one and that one. What happens is the whole spectrum shifts towards 0, and since these two are lower than the modulating frequency, what happens is they don't, yes, you can think of them as sliding past 0 into negative frequency region, but for our practical intents and purposes, what happens after that is they flip over back into the positive frequency region, just like here. And what used to be a high frequency ends up being a low frequency. What used to be a low frequency ends up being a high frequency. It's a mirror image flip called spectral inversion that happens in that case. These two spikes these two spikes represent the frequencies that were higher, these two, than the modulator frequency, which is set somewhere in here, and they are translated downwards by a difference of 18 kilohertz, and they look more or less the way they should look. But if this was human speech and we were to listen to this, it would sound something like the Mary Had a Little Lamb poem that I recited at the beginning of video number 1. Now, that's not necessarily something desirable from a speech perspective, but in the case of bats, we're not really listening to and trying to understand what they're saying. But in any event, if this sort of creeps into the audible region, a spectral inversion, we're really not getting a good representation of the ultrasonic spectrum. So it's probably in our interest to actually filter out frequencies, these frequencies that are lower than the local oscillator frequency, because we don't want them flipping over and becoming a mirror image, a spectral inverted mirror image of the sound. This is the sums frequencies, which we're not interested in anyways. We'll get rid of those by filtering. But just to sum things up, let's increase this numerical simulation modulator frequency to 35 kilohertz and see what the resulting output spectrum looks like. Oh, okay, this more or less resembles the amplitude ratios of 4, 3, 2, 1. A little bit better. This is all numerical simulations, and you don't exactly always get what you want. Okay, the modulated spectrum, well, here it is. The local oscillator frequency, also known as the carrier frequency, is at 35, and we have a mirror image different set of frequencies, and the sum frequencies are more or less still a representation of, but frequency translated representation of the original spectrum. So in this case, the difference frequency spectrum is completely mirrored. Okay, we're back here at the oscilloscope. Now, just to demonstrate the concept that I illustrated just a little while ago in MathCAD, this whole issue of spectral inversion, we will modulate the wine glass spectrum by 20 kilohertz. So 20 kilohertz local oscillator frequency, that is the upper audible limit of human hearing, and that should shift the audible spectrum and flip it, mirror flip it, invert it into the difference frequencies. region of the audible spectrum and create some frequencies that are not flipped. Oh, so two side bands. Okay, let's see what they look like. Okay, so that is the unmodulated input spectrum to the modulator. And now we can just change the source here and see what the modulated spectrum looks like. Okay, so the modulating frequency is set at 20 kilohertz there, and more or less this side looks like a mirror image of this side. So this is the shape, has the shape of the original spectrum, not flipped. This has the shape of the spectrum, mirror flipped. So let's see when we switch from channel 1 to channel 2 what the effect is. Okay, so that sort of gives you an idea how the upper spectrum is a shift of the original spectrum. So upper spectrum, upper sideband, lower sideband, but mirror reversed. So, well, that about concludes part 2 of the ultrasonic listening device. I had anticipated getting into the hardware nuts and bolts of the project at this stage, but we ran into an interesting technical glitch or difficulties, spectral inversion, that deserved a little bit more attention. So I hope you join me in part 3, and we'll get into the hardware there. I promise.